Hello everyone, welcome to the first lecture of the sixth module, which is on phase change memories. The disclaimers remain the same. So far, we have covered kind of 99% of the memory market that we discussed in lecture 1. So now let us try to understand 1% of this memory market which is left. And this market proportion may even increase to 10 to 20% in the near future. And why so? The reason being that you have several emerging applications like neuromorphic computing, hardware security, which are going to be really important in the future. And because of that, these emerging non-volatile memories can capture even 10 to 20% of the total memory market. So let us talk about one of those emerging non-volatile memories, which is your phase change memory. So before getting into the details of the phase change memories, let us look at this phase change material. So phase change memory is one of the oldest kind of memories which were established. So let me write this. So PCM is kind of one of the earliest established technology. However, it was not in the form of electrical phase change memory, but it was in the form of optical memories. And those optical memories comprise of CDs, DVDs, or even Blu-ray discs. So the 90s kids would be really aware about these CDs and DVDs and even Blu-ray discs because they would have played it. But even 2000 kids, I think that even they would have seen CD or DVD at some point of time. So we'll unravel the mystery behind the working of those CDs and DVDs through these lectures as well. So PCM is one of the earliest established technology, and it was started in 1968 itself by Ovshinsky. So what Ovshinsky observed is that in chalcogen alloys, so first of all, let me tell you what exactly are chalcogens. So let me just talk about chalcogens briefly. So chalcogens are nothing but group 16 elements. So what are group 16 elements? You have oxygen, you have sulfur, you have selenium, you have tellurium, you have polonium. So chalcogenides or chalcogen alloys kind of consists of these kind of materials. So what he observed was that these chalcogen alloys exist in two different states, in two different stable states. And what are those two different stable states? Those two different stable states are amorphous state and crystalline state. Now, what exactly is amorphous state? So, you may have also read about amorphous, crystalline, and polysilicon while discussing about silicon fabrication in your device fabrication course. You must have read about amorphous materials, polycrystalline materials, and single crystalline materials. So amorphous materials are nothing but they consist of atoms in disordered configuration. So amorphous materials consist of atoms in disordered manner, and since the atoms are arranged in a disordered fashion, they offer high resistance, and also in terms of optical property, they show a low reflectivity, or they are usually opaque. I won't say they are opaque, but yeah, they show usually low reflectivity. And what can we comment about crystalline materials? So the crystalline materials are usually arranged in a they're arranged in a periodic way, in a periodic fashion. So what are arranged in a periodic fashion? It's the atoms. So atoms are arranged in a periodic fashion in your crystalline elements, and they show a low resistance, and this resistance is the electrical resistance, and a high reflectivity. So this is about your chalcogenide or chalcogen alloys, which was studied by Oceansky. So he observed that there are these two different states, different stable states in which these phase change materials exist, and he also found out that these materials possess a large number of vacancies. So what are vacancies? Absence of some atoms, and the percentage was close to 20%. So on top of this, Ovchinsky also observed two interesting phenomena. So let me write that as well. So Ovchinsky also observed that these chalcogen alloys exhibit two different but interesting switching behavior. What are those two switching behaviors? So one of them is a volatile threshold switching behavior, and second one is non-volatile memory-like switching behavior. Let us now discuss these two switching behaviors in detail. So first of all, let us talk about this volatile threshold-like switching. So what Ovchinsky observed was that if you take a metal chalcogen alloy, metal kind of configuration, that is your chalcogen alloy is sandwiched between two metal layers. Let's say you start with the amorphous phase. I mean, the state of your chalcogen here is amorphous, and then you apply some voltage across this kind of configuration. So what you observed was that you started with some amorphous phase, and this configuration was giving you some resistance. This resistance would be high because the material is amorphous, is in the amorphous state, and it will offer a high series resistance. So you initially start with a very high series resistance, and we call this as, let's say, virgin or as deposited resistance. Okay, so we start with this, but as the applied voltage across this MCM configuration increases beyond a critical value, and that critical value is called the threshold. So as the voltage increases beyond the critical value, what happens is there is a sudden drop in the resistance. So at this point of time, I would also like to specify here that material or the phase change material or the chalcogen alloy is still in amorphous state. However, resistance has dropped. Moreover, what he observed was that if you remove the applied voltage very quickly. Then the phase change material gets back or returns to the initial virgin or as deposited resistance value. So you apply some voltage. As the voltage increases beyond some critical value, your resistance suddenly drops, but the material still remains in the amorphous state. However, if you remove that voltage very quickly, what happens is your phase change material again gets back to your initial state. And because this is not permanent change, we call this volatile switching. And this kind of switching is also called ovonic threshold switching, or OTS in short. Now let us look at the other kind of switching that Ovchinsky observed, which is like a permanent or a non-volatile type memory-like configuration, memory-like switching. So now let us talk about the memory-like non-volatile switching. So what happens here is, let's say you are again applying voltage across that MCM. So we apply a voltage across MCM. We increase the voltage. So as we increase the voltage, the moment it hits this critical value, what will happen? Its resistance drops. Now if we don't remove this voltage, what will happen? The current through this device will increase. So let me write that. So the current increases. Now as the current increases, there would be this Joule heating of the material. And if the Joule heating starts taking place, then temperature would increase. Now if you continue to increase the voltage, or if you continue to apply the voltage, so that there's this Joule heating and the material temperature increases, you can also hit the temperature may also increase beyond what is known as crystallization temperature. Let us call that as TC. So how do you change from amorphous state to crystalline state? You first provide a voltage. As you provide a voltage, because of this threshold switching, the resistance drops suddenly. And once the resistance drops suddenly, the current increases or it shoots up. And then Joule heating starts taking place. I mean, Joule heating was taking place even before this, but the current was very small because the virgin resistance is very high. But now that the current has increased, Joule heating has increased significantly, and the temperature of this phase change material increases rapidly. And now there is a temperature which is called the crystallization temperature. If you heat an amorphous material beyond this crystallization temperature and allow it to settle there for some time, let me just write that. So the temperature may increase beyond this crystalline temperature, and if we allow the material to remain at T greater than Tc for some time. So this is very important. We need to leave it above this Tc for some time. So it's not a very fast process. So amorphous to crystalline is not very fast process. So what we do, we heat it above this crystalline temperature and allow it to remain there for some time. So if we allow it to remain there for some time, what happens is, or if we allow it to cool very slowly, or allow it to, if we heat it beyond TC and allow it to cool very slowly, or if we let it remain there for a long time, then what happens? There is a change in the phase of material from amorphous to crystalline. How can you measure this change, or what are the properties that will change? So resistance will reduce significantly. So the resistance reduces significantly. And now, even if you remove the pulse, the material is still going to be in the crystalline state itself. So even if we remove the pulse now, material will remain in the crystalline state and continue to exhibit a small resistance. And since this kind of change is permanent, it is called a non-volatile switching. Now the question is, can we go back to the amorphous state from this crystalline state? Yes, we can do that. How? So to go back to amorphous state, from crystalline state, what we do? We heat the material. And how do we heat the material? Electrically, by passing a current. And relying on Joule heating. Relying on Joule heating. We can also increase the temperature optically by putting laser beams. So to go back from amorphous state to the crystalline state, what we do is we heat the material to what temperature? So we heat the material beyond its melting point. And let us kind of symbolize that by Tm. So we increase the temperature of the material beyond this Tm, that is, we heat it beyond this Tm, and then what we do is, like heating it to temperature above melting point is not sufficient. Then what we do is, we cool it rapidly. So if you cool it rapidly, the atoms won't find enough time to arrange themselves in a regular pattern. So you melt it and then you cool it rapidly. So this kind of process is called melt quenching, where you melt a material and then you cool it very rapidly so that you obtain an amorphous configuration. If you allow it to cool in a very slow manner, then again it will come back to your crystalline state. You can expect that it will be crystalline and not amorphous. But if you cool it very rapidly, you can ensure that it goes into the amorphous state. Now some phase change materials show another very interesting property. So let me write that. So some phase change materials also show insulator to metal transition. It is called IMT, insulator to metal transition. And how do we know that it's in the insulator phase or metal phase, or how do we even classify these materials in insulator or metal phase? So let me explain that as well. So what happens is, even when you change your material, phase change material from amorphous to crystalline phase, even when you do this, then still material continues to exhibit a negative temperature coefficient of resistivity. Which we usually call by alpha, right? Alpha T minus T naught. However, let me write that. So, however, if we increase the temperature beyond Tm and continue to increase it, or anneal the device or the material, it starts showing a positive temperature coefficient of resistivity. So this is property of metals, and a negative alpha is property of insulators. So since it changes its behavior from a negative coefficient of resistivity to a positive temperature coefficient of resistivity, this kind of switching is called insulator to metal transition. Also, we were discussing how we can change it from crystalline phase to amorphous phase and back to the amorphous phase. So we saw that electrically we can change it by passing current, and optically we can change it by heating it with a laser. But how we sense whether it is in crystalline form or amorphous form? So electrically we can sense using resistance, by measuring resistance, and optically what we measure is reflectance. So we have a small, like a low power laser beam. We apply it on the phase change material and we look at what is coming out of that. If it is highly reflective, then it's crystalline. If it is not reflective at all, it is amorphous. So that was about sensing. So we also saw that to convert it from amorphous state to crystalline state, we have to first increase the temperature beyond its crystalline temperature, Tc, and then let it remain there for some time. So the thing that it has to remain there for some time makes this crystallization a very slow process. So let me discuss about this. So what used to happen is, this crystallization time used to be the bottleneck. So although they were discovered in 1970s itself, right? 1968 you saw Shinsky came up with this. So they were discovered in 1970s itself, but from 1970s till early 1990s there was no commercial kind of application of this, just because there were no chalcogen alloys with fast crystallization time. So what changed in the early 1990s? So in 1987, people came up with this material which is Ge2 Sb2 Te5. In short, it's called GST. not the GST tax one, but this is called GST. And this GST material kind of transformed the entire PCM industry. So this led to drastic change in the landscape, and this led to the development of CDs, DVDs, and even Blu-ray discs. So Blu-ray discs are not actually GST. So let me write that as well. So for GST, the crystallization time was very low. And if you want even smaller crystallization time, you go for something which is called GT or GE2, TE2. And this was used in the Blu-ray discs. We'll read about their operation later in this lecture itself. But first of all, let us talk about this crystallization kinetics. And why we are talking about this? Because this was the limiting factor which hindered its development for more than 2 decades. So why exactly crystallization is slow? This we can understand only once we go through the crystallization kinetics. This is somewhat thermodynamics and somewhat chemistry is also involved here. Let us just go through it briefly. So crystallization of phase change materials consists of 2 processes. First process is nucleation and second process is growth. This is true for any kind of crystallization, but here even for phase change materials, nucleation and growth are 2 dynamics by which you can achieve crystallization. And nucleation can be of 2 types. So nucleation can be of 2 types. First, homogeneous. So what do you mean by homogeneous nucleation? If crystallization starts to take place inside the bulk of the material, inside bulk of phase change material. And then second is heterogeneous. When would you call it heterogeneous? If crystallization is occurring close to the interfaces, right? If it's occurring close to the interface or at the interface or at any defect. So defect centers also play a major role in enabling crystallization. And what exactly is nucleation? I mean, we discussed that it can be of 2 types, but what exactly is nucleation? So nucleation is nothing but attachment or detachment of atoms based on thermodynamic principles. So detachment cannot be called crystallization, but attachment of atoms. So let me just remove that. So it's attachment of atoms based on thermodynamic principles. So the moment we talk about thermodynamic principles, we have to talk about something which is called Gibbs free energy. So let me bring that Gibbs free energy into picture now. So what people observed was that number of clusters. What do you mean by clusters? So cluster of atoms, which are actually called nucleation centers. So such number of clusters were actually, so what people found was that the number of clusters of atoms of radius r can be given by a formula which is n of r, where n represents the number of clusters of radius r, is equal to n0. What is n0? N0 is total number of atoms in the amorphous state exponential minus del G divided by kb of t. So I brought this religious Gibbs free energy term here. So now let me discuss about that Gibbs free energy term as well, because that is really important. So that Gibbs free energy term, so that delta G term is the Gibbs free energy, and that is Gibbs free energy, like the component of this Gibbs free energy term, it's actually delta G, the differential Gibbs free energy, and that comprises of two components. The first component is the Gibbs free energy difference between your crystalline state and the amorphous state. And since you are also creating some crystalline amorphous interfaces, you also have to take into account the Gibbs free energy difference of those crystalline amorphous interfaces. So I'll write that it is the Gibbs free energy difference between crystalline state and the amorphous state, and the Gibbs free energy, energy resulting from creation of crystalline amorphous interfaces. So if you were to represent it mathematically, then what that means is your del G is a function of something. Let's call that minus GAC, which represents the Gibbs free energy difference between crystalline and amorphous state. And this is a volume kind of phenomena. So here we'll multiply it with the volume, where R is the radius. And then we have interface phenomena between crystalline and amorphous interface. And since this is interface, it is a surface area dependent component. Let's call this sigma as the energy resulting from creation of this interface, and then it needs to be multiplied by 4 pi r square, or the surface area. Now, why I am deriving these and why I am getting into details of this, you will get to know very soon. So the critical value of this radius, so we can find a critical radius RC when this term goes to 0, and that RC, or the critical radius, simply tells you that if you have clusters smaller than RC, then thermodynamically they won't be favored. They won't be favored, or they won't be stable. Let me say that they won't be stable, or they would be unstable, right? What about crystals? What about clusters having radius greater than RC? So if the radius is greater than RC, then those clusters would grow in size. And why they'll grow in size? Because they'll gain free energy. And why I have been discussing about this RC? I mean, if you look at it like this, there's no point discussing about these thermodynamic effects. But there is something. There is a relation to memories. What? You cannot scale, or scaling below this RC dimension is not viable. Why? Because it's not thermodynamically stable. If you scale it below RC, I mean, if your device dimension is less than RC, then you won't be able to nucleate. Then you won't be able to go from amorphous to crystalline. So that's the scaling limit. And that is why we have been talking so much about this RC and this Gibbs free energy. Now that we have discussed about this nucleation phenomena, let us discuss about the growth as well, because that is also a very important part of it. So first, there would be nucleation, and then there would be crystal growth. So let me talk about crystal growth. So where does this crystal growth happen? So crystal growth actually appears at amorphous crystalline interface, right? And the best part is, if you look at different phase change materials, different phenomena is dominant. Some may have nucleation dominant crystallization, some may have growth dominant crystallization. And how we can see that? So your crystalline phase has a higher mass density. So if you're looking at these materials using XRD or something, they will appear like dark spots. Any tool which shows you mass density of this like materials will show this crystalline phase to be having a higher mass density. So here in this diagram, you see two different materials. So on left hand side you have GST, and on right hand side you have GESP, or even GET is kind of the same kind of thing. So on left hand side, if you see for GST, you can see that there are many nucleation sites, right? So what these circles are, so what they did was, in an experiment, they kind of heated these regions using laser beam. So let me write it. So these circles are regions where they heated using laser beam. So your underlying thing is amorphous. Both of these are amorphous, and then what they did was they heated it with the help of laser beams at these 9 spots. And when they observed its like mass density, so as I told that crystalline has got a higher mass density, so they appear as dark sites. So what they observed was that in GST we have several of these small clusters nucleating. So what we can say about GST? It's nucleation dominant. And on the right hand side, if you compare it with GET or GESP, what you see here, there is only one nucleation site, and then it has grown a lot. So there was only one nucleation site and it has grown a lot. There is only one cluster and it has grown a lot. So this is growth dependent, growth dominant. However, for crystallization, both growth and nucleation have to be there. So let me write it. So for crystallization, both nucleation and growth are important. Now, what can we comment about these growth dominant materials and your nucleation dominant materials? So let me write some things from memory point of view. Let us say I have a phase change material which is nucleation dominant. So let us talk about nucleation dominant phase change material. So if it is nucleation dominant, what can we say about it? It's slower process, right? So in nucleation dominant, what we have is, since it's a slower process, so let me write it. So it's a slower process. Since nucleation is a slower process, we have a better control of resistance as the nucleation sites continue to grow. And what that leads to? This will give us better multi-level capability in terms of memories. However, at the same time, since nucleation can be at random places, and it's not something which is it's very confined process or something, so it will also lead to more variability. However, on the other hand, if you look at growth dominant materials, since growth is a fast process, you saw here same amount of laser beam hit all these materials, but here there were very small clusters which kind of came up in the case of GST, while large clusters came out in case of your growth dominant. So this is kind of fast, this is slow, but at the same time, since you have like many small like clusters, so just by using this laser beam twice or thrice, you can kind of convert particular regions of this into crystalline. So you can achieve multi-layer capability. But here you see that since it's high, like since the growth is very fast, you cannot achieve that multi-level capability. Since it's a fast process, so MLC is difficult. I mean, it's not impossible, but it's difficult simply because it's a very fast process. However, since here you are only like working with one nucleation center and then it's growing around it, so variability is expected to be low in this case. So these are different properties which you may expect out of nucleation dominant phase change materials and growth dominant phase change materials. And on top of that, the best part is that some of these phase change materials, so some phase change materials, they exhibit nucleation dominant crystallization at low temperatures, but P higher than Tc, but growth dominant mechanism at higher temperatures. But how much high temperature? That temperature should be still less than the melting point. So what this gives you a freedom to even tune into a regime where your nucleation is dominant mechanism or growth is the dominant mechanism. So you also have this kind of phenomenon which appears in some phase change materials. Okay. So now with this information, let me now unravel the mystery behind the working of rewritable optical storage disks. So on your left hand side, what you see here is a storage disk. It's an optical storage disk. So what we have here is we have layer of dielectric. So let me write it. So we have layer of PCM sandwiched between two dielectrics. On the figure on the left, we have like these two dielectric layers, and in between them we have PCM material which is kind of the recording layer. So this is the recording layer as it has already been pointed out. And then, so let me write it. So we have this dielectric layer on top which provides mechanical support. Then there is a dielectric layer which separates your PCM from a reflective layer. So you have a reflective layer at the bottom, which is shown here. And then this PCM is patterned, this PCM, not PC memory, this phase change material is patterned here in what is known as a crenellated shape. Why so? Because these, so let me just use a different ink. So these different sections represent different tracks. So different, I would say, trenches in phase change material represents different tracks. So this is your CD or DVD or Blu-ray disc, whatever you call it. So now how it works is, in your CD player or DVD player or even in your computers, you have something like this. You have a laser tester. This is called a laser tester. So let me write that. So on your players or on your readers, CD readers and all, you have something which is called laser tester. So this laser tester has two kinds of lasers. So let me just write that. So this laser tester has two types of lasers. One is high power laser. So what this high power laser does? So this high power laser, it simply heats it up and changes the phase. And then there's a low power laser. So what this low power laser does? So this low power laser does nothing, but it only reads the state or the phase. And how will it read it? It will read it by sensing the reflectance. So the low power laser does nothing, but it just reads it by measuring the reflectivity. And what we know is your crystalline phase has got higher reflectivity, and amorphous phase has got a lower reflectivity. However, now let us see how engineers think. However, we know for a fact that, crystallization is rate limiting or the bottleneck. Why? Because it's a slow process. So if we start with an amorphous phase change material in discs, it will take a long time to crystallize and write data on it, right? To work around that, what engineers proposed is, instead of starting with this amorphous phase change material, why not start with crystalline phase itself? When you start with a crystalline phase, what you do is you have to to write, you have to convert those crystalline phase into amorphous phase. So for that, what you need to do is you heat it above the melting temperature Tm and cool rapidly, or you melt quench it, which is a very fast process. So this is a very fast process. So if you melt quench it immediately, after heating it, then you end up writing amorphous phases. However, is there a trade-off? Yes, there is one. So amorphous to crystalline is less energy consuming. Why? Because Tc is much less than Tm. So in order to heat the material beyond Tc, you need a lower amount of current, but crystalline to amorphous is high energy consuming process. Why? Because you have to heat it to a temperature beyond this melting point and then quench it fast. However, this is very fast, but energy consuming. So if you start with a crystalline phase in your optical discs, you can do this writing very fast, but at the same time, it will consume a lot of energy. That is the reason your CD writers were not installed ever in your mobile phones. Size were also one constraint, but they could have installed it on your tablets, but they didn't do it just because, this is a very energy consuming process. Anyways, tablets were also not at that time, but even when tablets were, invented first, CDs were still prevalent. I mean, DVDs were still prevalent, but still they didn't go for it just because of this energy. So they started using this crystalline phase in your optical disc. So let me write that. So in your optical discs, you start with crystalline film. And since it's crystalline film, it's highly reflective. And that is why you see that shiny surface on, a very new CD or DVD. However, as you write it, so as you write data on it, what happens? Amorphous regions appear there. So it leads to those dark spots, which are not as reflective. And then that indicates that CD or DVD has been used or written. So if you look at any written CD or DVD, you will find that there are several lines on it. There would be several circular tracks or lines, and also there would be few scratches like thing. I mean, it would appear like scratch, but it's actually a data which is written there. So that is how you distinguished between a new CD and an already written CD. And another important point, in your rewritable DVDs and CDs, so if you also want this rewritable property, what does that mean? So you wrote something, so you started with crystalline. Then you wrote something, you wrote a data on your disk, you changed some track to amorphous. And now if you need to rewrite it, what it means is you will convert it to crystalline and then write whatever data you want to write. So here the best part is that even this amorphous to crystalline conversion is very fast. Why? Because, so let me write it here. If you start with a crystalline phase, even amorphous to crystalline transformation is very fast. Why? Because now you don't need nucleation, right? Let's say this is your disk. I mean, I've drawn a kind of area of a disk. This is entirely crystalline. And here you have amorphous region that you have injected by heating it with laser or something. So now if you want to change it to crystalline, you don't need nucleation. Why? Because growth can appear here. It is surrounded by crystalline material. So the crystalline phase or crystal growth may easily occur at interfaces. Since nucleation is not involved here, this is also very fast. So these kind of disks come with a rewritable property. And you see how engineers made your lives very simple and at the same time elegant.